So, hi everyone, welcome you all to DoK Explorers Day 2023. I hope you're all doing well and let's get started. So, I'm Harsh and I'm currently a mentee under Linux kernel mentorship program and I love playing around with cloud native technologies. I recently got my hands dirty on Kubernetes and this made me excited. So, today's topic of discussion is messaging in Kubernetes and we need to understand that why it is so important. So to start with, I'll share you some statistics. So Data on Kubernetes community does an annual survey where we actually interview the respondents who are running their data workloads on Kubernetes on various enterprise requirements and all other stuff that's relevant. So we surveyed industry leaders who were running the streaming and messaging workloads on Kubernetes, and 96% of them said that they were satisfied by deploying them on K8s. Out of these 96%, 55% were highly satisfied with what Kubernetes had to offer them. So let's start with a simple question. So, how do microservices communicate in Kubernetes? So, you might have guessed they send messages. Yeah, they send messages. Messages via API endpoints. Requests and responses via API endpoints as messages. That's it. There are various ways you can do this. You have this well-known HTTP REST standard, which is the de facto standard for most APIs that we are seeing today. Then you have another one, which is the gRPC. Then there are these well-known message brokers you have like RabbitMQ, etc. So you might say, "Ha, that's pretty obvious. Why should I need to bother about it?" Well, let's look at a problem statement. Suppose I want to build a distributed system. So what I do, I have two services, right? I'll keep track of the connections or the communication pathways, or rather, I should say, the API endpoints that I need to manage for communication between all the services. I need one connection if I have two services. I add one more, I need three connections. I add another one, I need six connections. I add one more, I need 10 connections. And I'll keep on adding, and these connections will increase. And now, mind you, let me remind you here all these endpoints right now, the type of architecture that I'm showing you is all managed by the application. That means the application developer needs to ensure that communication is going to be there with each and every service, how many endpoints they need to manage between two services. So to simplify this, I've actually plotted a graph for you. So you can see here for two as less as 200 services, we have scaled up to 20,000 connections. And most of the enterprises today run thousands of microservices over Kubernetes. And then if I need to manage these many number of connections, man, I'm in real trouble. Yes, the IT operations team is in real trouble. Your applications developers are going to be in real trouble. And they'll be doomed. And of course, the very essence of Kubernetes was designed to make distributed systems easier. And then if you have to run 10,000 microservices over Kubernetes, you are managing a humongous number of connections. That's the problem. And if you have ever taken a computer science course, you can actually easily figure out that the growth rate of the number of connections given the number of services is O of n square, which is not feasible, either technically and from enterprise point of view as well. And in fact, what we have achieved in this architecture, scaling up to thousands of services, is complete chaos. Why am I saying chaos? First off, the biggest challenge in this architecture is maintaining a coordination between the services. Then uh, being able to troubleshoot these services when there is a bug or there is a failure. Suppose there is a failure, you have 10,000 services, and then there's a failure in one service due to which the whole distributed system shuts down. Now, how are you going in production? In production, how are you going to check where did things go wrong, right? Which endpoint failed? You have 9 10,999 connections to check in each of the 10,000 services to figure out what failed. And that's what chaos is. And in fact, it can be a security concern. Let's see a hypothetical scenario. For example, I am running a social media website, and a user wants to update his profile picture, right? And due to some bug, what happens? The profile picture gets updated even before the request from the user's device is authorized by another service which was actually responsible for authorization and authentication. This is a hypothetical scenario, but it's perfectly possible, right? Given you have a bug or you have some sort of failure, if you run on this architecture, and this is a security concern, this can be utilized by malicious attackers to compromise your systems. So how do we solve all these problems? Well, let's welcome message queue. So I'm not going into formal definitions right now. You can read it. So what I'll focus on 2 points is that it's a central point for asynchronously sharing messages, right? So I'm going to focus on these two keywords, central point and asynchronous. So what we need is that we need some sort of a middleman which can manage all these connections for us and all the communications for us. And that is what is achieved by message queue. A message queue in itself has a lot of queues inside it, and these queues are generally called topics. Now, what happens is every topic connects two distinct types of services. And these services, on the one end, you have services called the producers. On the other hand, you have services called the workers. What producers are? Producers take in the request from other services or takes in the request from users and publishes that request on the message queue. Now, what message queue does is it's very much like a queue, right? In suppose you want to buy tickets for a movie in a cinema hall. What happens? You stand in a queue. The one who gets first in the queue gets the ticket first. That's in first in and first out. And that's the very essence of a message queue. These producers publish messages in the queue, and these workers pick up these messages one by one, process it, and then either serve the response to the users, or if that data needs to be sent to other services, it's sent. Now, coming to the point of asynchronous communication, suppose even though your application might not be designed for asynchronous for serving asynchronous requests, but with message queues, you can actually turn your synchronous applications into asynchronous ones. Suppose let me show you via this diagram, right? You have these producers. One producer can be my server in India, the other producer can be my server in the US, the third producer can be my server in Australia. Now, what happens? Requests from these users come in and they are published into the message queue. Now, you have the replicas of various of the other worker service, many replicas of it that are running. Now, these messages are distributed by the message queue among these workers, right? Such that no worker takes in all the requests. It does all the load balancing by itself. That's called scheduling. All the scheduling is being managed by it, and this actually ensures consistency. It ensures that your resources are not overloaded, so you can actually have greater response times as well. Now, since more than one request is being taken up by the worker services and is processed at the same time, you can have asynchronous communication. How cool is that? Even though your application was not designed to be asynchronous. In fact, if I zoom out in this architecture, what from the application developer's point of view, what they need to really manage now is the connection between their service and the message queue. That's it. So, in effectively, they need to manage as many connections as there are services. That is, for n services, I will have n connections. That means I can scale linearly. I don't need to worry about how I'm going to communicate with the all other services in the architecture, because all that hassle is taken up by the message queue. It's responsible for all my scheduling, it's responsible for all my load balancing, it's responsible for all my connections. It's doing all that stuff. How great is that? Now, as I talked about asynchronous requests, so that will actually enhance the user experience as well. Because now my service is asynchronous, I can have faster response times, I can have slower wait times. And coming to the security part, what we have actually enabled is eventual consistency. So let me break this down for you. What eventual consistency is that no data entity will be served to the users once it has been updated on all nodes across the network. Let me that is that if an update is being done, right? Let's take that example of profile picture. Until and unless my request my has been authorized by the authentication service, my profile picture will not be updated. It will not, and that change will not be replicated across all the servers. And once my profile picture has been updated, it will not be shown to the users until and unless that change has been replicated across all the servers. So what it is effectively giving you, it's giving consistency in terms of your data. You are actually maintaining your data integrity as well. How cool is that? Let's talking of some implementations. You have some in-house message queues such as RabbitMQ, very famous one, and then you have Kafka. Well, Kafka is much more than a message queue, but it can be used as a message queue. And then you can use in-memory databases such as Redis as message queues as well. But like every engineering solution, message queues come with their own problems. And running message queues on Kubernetes, specifically on Kubernetes, is not easy, because Kubernetes was designed for microservices. And what are microservices? Are light, they are stateless, they are horizontally scalable. But message queue, on the other hand, has to manage scheduling, has to manage how messages are being distributed, has to do a lot of processing. That means it's resource heavy. And then if it's dealing with data, it's managing messages, and that data has to be stored somewhere. Then it has to compensate for the response times as well. All that stuff means it needs some sort of data storage. That means that makes it stateful. And if it's stateful, that means it's going to be vertically scalable. And this is very much different from for what Kubernetes was originally designed for. And that makes it a little challenging to deploy message queues on Kubernetes. And there are mitigations for the same, right? If you've been there with the DoK Explorer stay since the beginning, there have been talks on operators as well, and we have been covering operators for a long time. Make sure to check it out. So what operators actually allow you that they actually ease off a lot of deployment stuff, right? For example, uh, I want to deploy RabbitMQ message queue on my distributed system. What I need stateful sets. I need to configure deployment. I need to configure my persistent volume claims. I need to configure my stateful sets and lot of other stuff. And then all this does not cover the edge cases that can happen, or the network failures that can happen. So all this application level intelligence is baked into operators, and this can be managed by operators, making it easy to deploy, and it will take care of all the edge cases that can happen. How cool is that? But there is an even better solution that I'm going to show you. Is using something that is tightly integrated with Kubernetes. Introducing KubeMQ. It's a CNCF project, and it's a native K8s message queue. So being native means that I don't need to get into the hassle of too much configuration, because it's already built in with Kubernetes. And that means I can have a lot of day one convenience. And being native means that it's being K8s native implies that it's optimized to run with Kubernetes. And if it's optimized, it's going to be lightweight. And if it's going to be lightweight, it can save a lot of enterprises' resources on the cloud. And especially for the enterprises which are running on multi cloud ecosystems, it can actually reduce the total cost of ownership. And best of all, that this message queue is designed to be extensible, right? You can connect to a variety of other applications and services, reducing the need for custom integrations. And this is achieved via a lot of connectors like bridges, targets, and sources. So, yeah, that was a lot, folks. So, if you want to go into more details or want to learn how is data on Kubernetes revolutionizing the cloud native space, you should get our hands on the 2022 report. And for further queries, I'm available on Slack. Go hit the link in the description, join our community Slack, and I'm going to answer all your queries there. You can contact me on my social handles here. So, thank you all for joining in, and I hope you enjoyed the session. Ta da!